Okay, welcome back everybody, and to the second session of this semester. I just wanted to, like yesterday, repeat some of the practicalities. So you will find all the kind of public information, essentially all messages and educational material from the official website. And for those of you who may not have studied here at the University of Oslo, if you look at the schedule, you can actually subscribe to these activities. So that means that any change I make is something you can get either by email or by a text message. So that's in case there are changes in lecture hall or whatever, because sometimes there may be construction work like yesterday and we may have to change and so on. So that's one of the things. And the other thing is that the messages and so on, you will find them here. There is a link to a Zoom link, which you can use in case you cannot be here for different reasons, or you can just watch the recording. And these messages, you will find these messages about the weekly plan, both under the Canvas site. So there will be an announcement like this. And then, so this contains also a link to the video from yesterday. So you will also find the same link. So that will typically be uploaded if you go to the schedule, and then you look at lectures here, and then you will find the video of the lecture. So that's normally uploaded afterwards. And I use YouTube to generate subtitles. And subtitles normally take a little bit more time, even if they have invested a lot of machine learning funds to improve their processing. So this is an automatic processing, which means that when you do more specialized things like many-body physics, there may be some funny words. So like Feynman is often translated into fireman, and many-body becomes many-money. And so there will be many. I will not edit these subtitles because it takes a lot of time. So you can have some fun. Whereas if you teach machine learning, it does a fantastic job. So even on complicated names, which are used in the machine learning literature, it gets them correctly. But this is a topic which probably has not entered the standard machine learning training of different languages. And if you can actually then, if you don't want to have an English, Google allows you to translate to Norwegian if you want that. So I normally do that because we have people with, hearing impairments, and then it's often nice to have subtitles. And also my English is much Latinized, which also means that there may be words which not everybody has used. Okay. So that was just a little bit of practicalities, and then you have the GitHub site. So if you go here, you will find a link to all the teaching material. And as I mentioned yesterday, you will find the weekly material. If you then just go to the pub folder, public, and then scroll down to week 34, you will find either PDF, Jupyter Notebook, or the HTML variant. So this is up to you which one you want to use. And you will also find in the same page, you'll find the, if you just move up a little bit, you will find exercises for this year. If you go to the handwritten notes, this is a place where I will put in the notes for every week. So these are essentially the notes which I add to the slides which I have. So I will often in the beginning, since we have some repetition of things you've seen before, I will mix the whiteboard with slides. But for many lectures, I will just use whiteboard, which is just my substitute for the blackboard. And with these modern gadgets, you can save the file and then you can have the whiteboard notes after the lecture. So, and then there are, in the literature, you will find these textbooks like Sabon Oslund, which I follow in the beginning. And then we also have the textbook by Shavit and Bartlett. So they happen to end up here in a magical way. I don't know how they ended there. They just ended there. I don't have a lax attitude to copyright, but it may seem like I have a lax activity to copyright. It's up to you to decide what is meant by a lax attitude. Actually, these books, if you search, I think I mentioned yesterday, sometimes the PDF version appears online before the publisher has published the book. That has happened in some cases. Okay. The other thing is that publishers like Springer, I don't know how familiar you are with that, so I just wanted to mention it. So the university now has agreements with most of the publishing houses. So like Springer, when we, as a university, we pay millions of Norwegian kroner every year. So you get a bundle of the scientific articles, journals, and textbooks. So if I find that Springer textbook, I will typically just take the PDF and place it online. Like you have here, if you go to literature, this textbook here is a textbook on density functional theory, which you can access for free if you use a University of Oslo IP number. The same applies to other publishers like Cambridge and Oxford. All their new textbooks are books which you can access for free if they have made an electronic version. And that's a fantastic service because many of the publishers, they actually have realized that when people take the electronic version, it hasn't reduced their sales because many people like to have the book itself. And then you can just skim through the PDF file. And if you like it, you buy it. So it's in a way, it's a kind of teaser, right? You see the book and then I like to have the books on the PDF, on the iPad. But then I also buy the printed version as well. So that's just a kind of service which you should make use of. So any new textbook from many of these big publishers like Wiley, Addison Wesley, Oxford, Cambridge, Springer, Elsevier, you will find them for free from the university library. Okay, that was just a little bit background about literature. And I just wanted to go back now to the notes. So let me just bring up the notes from yesterday. So let's do that. So one of the things which we did yesterday was to go through some of the basic linear algebra which we need for quantum mechanics. And I'm just going to catch up some of these elements, and then we're going to dive into the blackboard, whiteboard after that. So let's just quickly bring back where we were yesterday. So I'm not going to repeat these things, but you can actually look through them. These are basic linear algebra elements. And one of the things we did was to define what we call a computational basis. And yesterday we discussed an example like the harmonic oscillator wave functions, which is a handy basis. It can be a solution to parts of a many-body problem. So you can use that as a computational basis. It provides you with an orthogonal and normalized basis, or an ONB, as we will use as an acronym for the rest of the semester. And these are two typical examples. So yesterday we looked at the case of a two-level system, which you will also see in the exercises next week. And in this particular case, you could just think of these as two orthogonal states. And with that, we defined also important operators. We defined these projection operators, which have the properties that p squared is equal to p. So these are idempotent operators. P times q is equal to 0. And p and q commute. So that's also a very important property. So that means that they have a common eigenbasis as well. And we will also later see that p and q commute with the Hamiltonians which we have. So that is an assumption which we are going to put in the models which we develop. So in this case, we have a very simple completeness relation, since our Hilbert space contains just two states. And then, but in principle, this is infinite. And all of many-body physics, as we discussed yesterday, deals with us trying to find approximations to an infinite set of degrees of freedom. So in our case, the degrees of freedom are represented by these two states. If you solve a one-particle problem for harmonic oscillator, then you have in principle an infinite set of eigenpairs or eigensolutions to the harmonic oscillator problem. So we mentioned that yesterday, P and P times Q, they are P multiplied with Q is 0, and the commutator between P and Q. So if you need to repeat what a commutator is, just think of you writing matrix A times matrix B minus matrix B times matrix A. That is not necessarily equal to 0. And that defines a commutator. Anyone who doesn't remember what a commutator is? Okay. I hope I'm not offending people here, right? So there are some famous matrices, which we will also use in some occasions, for examples later. And for those of you who have studied or will study quantum computing, these matrices play an important role because you actually rewrite many of the operations on quantum mechanical systems in terms of Pauli matrices. So if you're interested, we can discuss that later. But also we have courses on quantum computing where one elaborates on the importance of Pauli matrices. And these are also examples of matrices which have some important properties, and they have a commutation relation, which you also probably have seen. So this is just an example of some of the matrices which we will encounter. And in one of the exercises, we are going to encounter a model which is called the Lipkin model. And some of you, I mean, Jon, you may have heard of that from nuclear physics. It's a popular model in nuclear physics. And there you can actually rewrite the Hamiltonian in terms of the Pauli matrices. But that's for later. Now, as we also discussed yesterday, you can expand when you have an orthogonal basis. You can then define a new basis. And normally, as we said yesterday, this orthogonal basis is often a basis which we choose as a solution to a specific problem, which we can solve. And preferentially, we can solve it in terms of analytical results. So we get analytical solutions, or solutions which can be solved numerically easily. And in some cases, you may even have closed form solutions, but that's more seldom. Normally, you have an analytical expression in terms of functions which you have to program. So for the harmonic oscillator, it's a Hermite polynomials multiplied with an exponential with argument minus x squared, for instance, in one dimension. So that means that you can construct a new basis, which is just a superposition of these. And then we know that these two quantities actually equal alpha and beta are equal to the overlap. And as we said yesterday, many-body physics deals actually with finding these coefficients, and you have different recipes for doing that, alpha and beta. So normally you don't know psi, you know this state, and you know this other state, and you don't know alpha and beta. And that's essentially the overarching message about many-body physics. Different ways of finding this function on the left-hand side of the equation. And we have the inner products. So we will repeatedly use the standard Dirac bracket notation instead of writing these as vectors. So one of the exercises is actually about showing the preservation of orthogonality. So if you now also act with these, as we discussed yesterday, so this is a quick summary of what we did yesterday at the end. If you act with these operators, these projection operators, you actually project out one of the states. And these operators are actually used to make a rigorous mathematical approximation between the infinite space and an effective smaller space. And the smaller space can often be defined by this operator P, which then will define your effective Hamiltonian or effective quantum mechanical operators which act in a specific space. And then, depending on what kind of many-body theory you deal with, you will express the degrees of freedom which you have left out through this operator Q. And many-body perturbation theory, which we are going to meet, is just one of the examples where you can construct in a systematic way a reduction of the total Hilbert space to a small effective space, which you can handle computationally. And sometimes even by paper and pencil. Another quantity which we will encounter, which we are going to study as well, is the density matrix. Have you met that? If you're taking a course like Physics 4110, then the density matrix is a standard ingredient. And that is a quantity which we will meet again and again. So I'm just reminding you of that. So the density matrix is simply the outer product for a given state. So this state could be the ground state of a system. It could be an excited state. And this is something which you then, when you do the algebra, you get this matrix here. And when you take the trace of it, then you should preserve this kind of norm of the states. So the trace of the density matrix gives you the norm of this new state, which you're looking at. So these are quantities which we will work with. We're going to repeat some of this. You will see that in different disguises when we run calculations. And it gives often a very compact way of presenting a quantum mechanical set of expectation values, for instance. If you're doing quantum computing, as some of you may end up doing that, then the density matrix plays a central role, and it's often linked with quantities like the information entropy, which is also used to study entanglement, or in Norwegian sammenfiltring, which is an important property in quantum mechanical systems. Then there's another thing, and this is important for the notation which will come. So when we are thinking of specific states, let me just take these examples here and then just bring in another example. So we have two given states, two vectors. Now, normally what we write, this is a compact notation, is this xy which you see here, but that stands for the tensor product of x vector with y vector. But clearly you don't want to carry this notation with you if you have, let's say, suppose this is particle 1 and this is particle 2, then you want to have a more compact notation. So when we are going to write states now, we will write states in this specific way, but then we have to be careful with what that means. So that means actually this, what you see here, a tensor product between different states. Okay? This is something which we often have forgotten because we get so used to this notation, but what it means is actually, it means actually this. So when you have a Hilbert space with 10 particles, your total state, which you define, will be the tensor product of 10 particles. So if we take these simple examples and we take two particles, or this two level state which we have, and we want to make a new state which now contains info. So we can now think of this as particle 1 and this as particle 2. So this will be the Hilbert space in this two-level system. So you can think of placing two particles in a two-level system. So if we now want to exemplify that, so let's just go back to the so let me bring up that one so it becomes a little bit easier to see that. So the way you can think of this now, if you go back to the example we had yesterday with this two-level system. So we have a level epsilon 0 and epsilon 1. Now, what we did yesterday was that we could think of this as a many-body state, a complicated state, which is in a many-body system, or we could think of this as just a single particle state. So now we're going to do that just for the sake of simplicity. And we're also going to assume that these are spinless particles. So that means that we can have a particle here. And if we insist on doing something as artificial as fermions, which are spinless, which is an artificial thing, then we can only have one fermion in one slot. That is a consequence of the Pauli principle, which says that the total wave function has to be antisymmetric. So what you could think of now is that we give this dude here the red color, so this is particle 1. And then we know that particle 1 could also be in the other state. So we could have it here. And then what we are saying is that this particle 1, which I'm labeling as X here, that can have two states. It can have the state 1, 0, which we now let represent that state, or it can have the state 0, 1, which we just use as one possible way of setting up the orthonormal basis for one particle. Okay, so that represents this one. So that's the other state of the system. And now you could say that, okay, if we add the spin, we could then have spin up and spin down for the particles. Or you could now think of this system. So we could call this system A. And then we could call the next one system B. Okay? So in system B, we have exactly the same states, but they are two different systems. So you would have an epsilon 0, an epsilon 1, and then you would have a new particle. So now we put in a black color here. So this is system B, but we use the same states. So this would be 1, 0, and 0, 1. And I simply say that this is state Y. And Y can be one of these two options, okay? So now I could think of putting these systems together. So what you could think of now is a system which looks like this. And this is actually an experimental realization in condensed matter physics. When people are thinking of using systems like quantum dots, which are electrons confined in small areas, and using them to actually perform quantum operations on these systems, you actually manipulate an experimental system. So you could think of having, for instance, an electron, which is here, and this is system A, and then you have another realization where you have system B, where you also have the particles. So we should actually keep red here, and then we have black here. Not that one, but this one. So that state, which now becomes X, tensor product with Y, is actually given by this state 1, 0. Maybe I should keep these colors because I belong to this kind of colorblind people, but now I can play around with color. So this is actually given, and then this one is in black, or 1, 0. So that would be the state of the system AB. So this should be equal to XY and corresponding to system A and B, or we just write it as X and Y. So that is the kind of shorthand notation. Now, these are systems which you can realize with systems of semiconductors. And they actually do make them at the Center for Material Science. So these are systems which are being studied by them. They can find the candidate systems where you have two distinct levels. You have many more in addition to those. But you can idealize everything and say that this is now my effective Hilbert space. And I want to study a system of two electrons where each electron is trapped in a small area. These are why they're called quantum dots. People have made them in the lab, and they're normally called artificial atoms. So they display many of the properties like the atoms in the periodic system with magic numbers, etc. They do actually that. This is pretty cute. There are lots of cute experiments in semiconductor physics which move along this axis. And this is the reason why I bring it in is just an example of how to say we combine these orthonormal basis sets to now construct a two-body system. So this is a two-body system. And then you would have a Hamiltonian acting on a two-body system. And these two electrons could then interact, either by the Coulomb force or perhaps some other force which you would apply. So this becomes then an interacting system. But each by themselves, you could think of them being decoupled from the environment, and you could think of being able to find an analytical solution for X and Y. And this is normally the case which we end up doing in many-body physics. And that would be your computational basis. And then you put on the interaction, and then you find the fully interacting wave function for the system. Okay, that sound okay? So I just bring in this kind of examples back and forth, because that hopefully allows you, as I normally say, to see the wood for the trees. So let's go back to the slides, because there are some technicalities which I want just to repeat so that we have everything here. Let me see, where do I have my slides? Yeah, sometimes they actually disappear. Okay, so let me see now. It should, now let me, has always been the problem when I switch back to the slides. Sometimes they don't show up here. Okay, so let me reduce that one. Okay, and then we go back. Did you see it? No, that's just notes actually. Oh, there it is. This is me not seeing. Thanks. Too many windows open. Sorry for that. Anyway, this will be the mathematical form which you actually end up with. But we will always use this kind of compressed notations like this, 0, 0, 0, 1. And then obviously you can make the other combinations here. So now you see that with a binary system, when you combine two, you obviously get 4 possibilities. And the probability also, if you think of measurements, these projection operators, they play actually an important role. And when you do quantum computing, you often deal with these type of projection operators to define gates. So you can actually, if you do a measurement, then this state, which is in a superposition, yields actually just one of the states when you make a measurement. And they have a given probability. So I'm going to just leave out some of these things. One of the things I also wanted to remind you of is that essentially all the operations we would deal with Hermitian matrices. The matrices are going to be square matrices, and they're going to be Hermitian in most cases. And when we are looking at these transformations, which we discussed yesterday in more general terms, in many-body physics, what we often want to find are these coefficients. And these are normally given by unitary matrices. So this will be the matrix elements of a unitary transformation. And as we also said yesterday, it's normal when you build up a total wave function to actually start with a single particle picture. So many of the methods which we are going to discuss, they apply well to systems where single particle degrees of freedom make sense. So that means that you can make a measurement and you can make an interpretation of the data in terms of single particle properties. I mean, a single particle property is not an observable. You have a many-body system, so there is nothing like a single particle energy. That is a theoretical construction. But you can extract expectation values which may be dominated by single particle properties. So nuclear physics and atomic physics are examples of that. In nuclear physics, there's something which is called magnetic moments, which you can calculate by just thinking of the magnetic moment of one proton or neutron. And when you do a many-body calculation, this result will be pretty close to the one you get from a plain single particle picture, where you have no interaction between the particles. So you have observables which have these properties, which then motivate using a single particle basis as a starting point. But if you go to strongly interacting systems like quantum liquids, so that is typically the situation when you're looking at a quantum liquid of helium. These are systems which undergo a phase transition at very low temperatures to a superfluid phase. These are systems which are strongly interacting. And these kind of pictures, they don't make a sense at all. There are no experimental properties which can be related to these features. Essentially because a phase transition is a macroscopic phenomenon based on all the constituents participating. So phase transitions are system or physical processes where such a mean field picture doesn't make sense. Actually, we normally talk about the collapse of a single particle or mean field picture. And phase transitions are in general collective phenomena. And then these are much more difficult to describe by these degrees of freedom. So just keep that in mind. If you want to apply the theories which we deal with here to studies of phase transitions, just beware that they are not suitable for that. So one thing for the exercises this week, I'm going to quickly just go through this. There's a demonstration of unitary transformations and that you preserve orthogonality. So just take a look at these slides when you start looking at the exercises. So I will just flash through this. I won't do anything with that. I will just ask you to take a look at it because this is linked with one of the exercises about a reminder about linear algebra. And as we said, these unitary matrices, they have these properties here that when we take the Hermitian conjugate with the matrix itself, it gives us the identity matrix. I'm going to skip some of these things, I mean, because this applies to the exercises as well. This is a little bit more about orthogonality. And I want you to look up this when you look at the exercises. So it's a kind of hint for the exercises. So what I actually want to do now is to switch back to the whiteboard. And then we are going to look at the definitions of Hamiltonians. And we are going to set up also definitions of specific quantities, which I'm going to call matrix elements, but which are actually integrals. So we are going to define some compact notations. And we are also going to run some simple calculations for a two-particle system. And then from that, we are going to move to an n-particle system of fermions. So we are going to deal with fermions now, okay? So that means that if we follow Pauli's principle, the total wave function has to be antisymmetric. Now, one ansatz. So, and now we are coming back to the things which we discussed yesterday. So this is again a little bit of what we mentioned. A standard way of making an assumption about your system is actually to assume that there is one part, this H0, which typically can be solved analytically, or has solutions which mimic essential features of your system. So if you think of an atom like neon, it is pretty common to assume that an electron is very much dominated by the field which is set up by the atomic nucleus. So that means that you could think of that as one electron outside an atomic nucleus. And then you have in atomic neon, you have 10 electrons. So if you look at one electron, there's a field from the nucleus, which gives attraction. So you have a charge of 10 protons, and then you have 9 electrons. So the 10 protons give a very important contribution to the total energy. And then you have the repulsion between the electrons. So that means that if I leave the repulsion between electrons in this term here, then I could solve a problem where I have one electron which just sees the atomic nucleus. And that's a problem we can solve analytically. And you've seen that when you took a basic course in quantum mechanics, and that gives you the hydrogen-like wave functions, which are given by a Laguerre polynomial times an exponential with minus r, the radius, multiplied with a spherical harmonics. So that's a three-dimensional solution. And then we have a nice analytical solution, which we then can use as an ansatz. So when we now are constructing the total wave function, we're actually going to make an ansatz. And that ansatz is often the solution of a part of the problem. And with that ansatz, we are going to construct a linear combination of these states, and we're going to use that one to diagonalize, for instance, the whole problem here. That's one way of thinking, okay? And there's also another thing. So this P here, it has a hat on it to distinguish it from the projection operators. This is a permutation operator. So let's start looking at fermions now. So one of the things you can show, so I'm just stating this now, I'm not proving it. If you want to prove it, actually there are textbooks which I can guide you to. You can actually prove that if you make an assumption that the Hamiltonian is invariant under the change of the positions of two particles, and we are assuming that because we are dealing with indistinguishable particles. If we do that, then this Hamiltonian is invariant under the positions of particles. If I just interchange two particles, I get the same energy. That's a very important property. That's a symmetry which we are going to assume with all the Hamiltonians we have. Invariance under interchange of particles. There is actually no experimental evidence that this symmetry is broken. Okay? So this is a fundamental assumption we make about the Hamiltonians. Now, this guy here commutes. You can actually show that if you have an operator which is invariant under the interchange of two particles, and you have an operator which just interchanges the positions of two particles, these two operators commute. So I'm just stating this. I'm not giving you the proofs, but you can find the proofs in general textbooks in many-body physics. So this has an important consequence. And now we are going to go back to the whiteboard here. So one of the things which we will be doing now is to make some basic assumptions about the Hamiltonian systems which we have and the states. So we are going to look at the fermionic systems. Later, we will look at the total wave function for bosons. So in that specific case, what we have now, and I'm going to use different notations. So when you see a wave function psi like this, an uppercase letter, this is a many-body wave function. So this is a many-body wave function for a given state lambda, and it contains the positions of the different particles. So I'm just leaving this as particle 1, particle 2, up to xn. I'm going to specify some of the notations which I have here. And these are additional quantum numbers which we can have, which I just leave unspecified. So in our case now, these are the positions or the degrees of freedom which describe a single particle. So this is positions and other quantum numbers. Defining a given fermion. And here we can make an example now. And this could be a spin-half fermion. So that means that this x of I is actually now going to be given by the positions of the particle. And I'm putting a sign, a vector sign here to indicate that even if I have normally when you have a subscript, when I have a subscript without a vector sign, this is just one of the components. So that could be the x, the y, or the z component. But now I'm putting a vector sign. So this is the either the 1, 2, 3-dimensional position of a given particle. And then it has also a spin, so which I write like this. So that means that the wave function which you have, which also includes spin, is a tensor product of the spin degrees of freedom with the spatial degrees of freedom. So if I now think of a single particle state like this, I, which is defined like x of I, this is going to be the spatial degrees of freedom, which will then be an R of I. And then there's a tensor product with the spin degrees of freedom. And this contains sigma of I, and then it has a spin projection of I. So this sigma of I could be equal to 1/2. And that means that this projection can be equal to plus minus 1/2. So they live in different spaces, but the total wave function is normally written like that. And if we then want to use this compact Dirac notation, what you will often see then, if we do that, is that we have a notation like this, x of I, like that. That would be the compact notation for that specific state when I use a Dirac representation. So I'm putting an arrow because it's not an equivalent. There's not an equivalence there. But in principle, when we look at the single particle degrees of freedom, they're actually given by the tensor product for fermions of the spin degrees of freedom. That's one space. So if you're only dealing with spin, it will just be the spin degrees of freedom. So if you have 2 electrons now, with 2 electrons, you will take the tensor product of 1 electron here and the other electron, which then has the tensor products with the spin space as well, and the spatial degrees of freedom. Okay? So this is just to bring up the kind of notation which we're going to use. So when I write this x of I leave specific degrees of freedom unspecified. This could be a one-dimensional spinless particle or a one-dimensional spin-half particle. Now we're going to assume that we have fermions. Okay? So this is when I use this letter psi, this is so when I use this notation here, I'm going to refer to this as the exact wave function or the exact state of the system. So when you see that one, I have a Hamiltonian which acts on this psi lambda. And when you see this psi as an upper case letter, it means a many-body wave function. If you see a lower case letter, like those which you see here, these are single particle wave functions. Okay? So I'm going to make an ansatz now where I assume that this is an eigenstate of the full Hamiltonian. Now, what we know from the Pauli principle for a system of fermions is that if I interchange 2 particles, so if I operate on, let's say, interchanging particle I and j, so this is this operator which permutes 2 particles, and I act on this wave function, which is in a given state, a total quantum mechanical state. So lambda stands for the quantum mechanical quantum numbers which specify a specific many-body state. So there are a lot of small levels here which we build up upon. So then I would have an x1, x2, and then I have an xi, and xj, and then this moves on up to x of n. So I use uppercase letter n to indicate that I have n particles. So this one, when I have fermions, this is actually going to be given by minus psi of lambda of x1, x2, and then I have xj, xi, and then I have interchanged eventually spin or just the position of the particles. Okay? So this is the Pauli principle. This is an ansatz and about a wave function for fermions. And it was actually, its success lies also in the fact that you could describe the periodic system by assuming this. And experimentally, there is still no experiment which violates the Pauli principle for systems of fermions to what we might call experimental precision. So we believe that a system of fermions is a system which is governed by a total wave function which is antisymmetric. Okay? Yeah?
In this context, since you're swapping the position of two particles, that means that the order of your x's inside of this parenthesis has to be important.
Yeah.
So xj doesn't mean the position of the j particle.
No. The way you have ordered things. Exactly. Yeah. Yeah, yeah, exactly. So, and you will see now, because now we're going to make an ansatz for the total wave function. And the ansatz is given, so one way to implement this mathematically, ansatz, and this is, it's a very important thing, I'm just putting uppercase letter. This is based on a single particle ansatz for the total wave function, on a single particle picture. So the ansatz is that we now let this psi lambda, which is the solution to the many-body problem, we let this be represented by a phi uppercase letter, lambda. And this contains the same set of quantum numbers up to xn. There may be other types of unspecified quantum numbers, which we don't specify now. So this will be the ansatz which we are going to make. And one way to do that is actually to use a determinant. Because you know that when you interchange two columns or two rows in a determinant, that changes sign. So that's an ansatz. And the thing is that this ansatz which we have here, when we act with this Hamiltonian here, and we will show that pretty soon, when we make this ansatz, the idea now is that this is an eigen function of this reduced part of the Hamiltonian. So we're splitting the Hamiltonian into a, I didn't put it up here, so let me just remind you, because we take the full Hamiltonian and we write that in terms of one operator, and then one which is often representing the interaction piece. So the ansatz has the correct symmetry, and it's the eigenstate of a part of the Hamiltonian. So that means that we are going to have an eigenstate, which I label with an uppercase epsilon, multiplied with this phi of lambda. And we are going to show that this is actually the case in just a few moments here. So what you have now is actually the total wave function, which has been reduced on ansatz. Now, we are also assuming the following, so that this phi of lambda is an orthonormal basis, and ONB. So that means the following. It means now that I can calculate this psi of lambda here in terms of an expansion over coefficients, and I'm going to call this for delta equal 0, and in principle to infinity. That's in principle, okay? And that means that there are going to be some coefficients, C lambda, the overlap, delta, and then multiplied with this orthonormal basis, which I have defined. So I'm making an assumption now that my, no, not lambda, sorry, that was wrong. This should be a delta, like that. So I'm defining an orthonormal basis as the solution to a part of the problem. And now this is not a single particle state, but it is a many-body state. But I'm going to construct an ansatz here, which is given in terms of single particle states. So let me just bring that up. So this H0 is an operator now, which is going to be a sum from I equal 1 up to the number of particles. as a function of a one-body operator. And this is a function of these variables x of I. It could be spin, it could be position, whatever. So this is now a one-body operator. And yesterday we mentioned an example like the harmonic oscillator. So an example which we looked at yesterday was this x of I here. And that was given by the harmonic oscillator in one dimension, 2m, and then I have a d. And now I should be a little bit careful because x, I'm leaving out spin. So there's no spin dependence. So I just have a dependence on x plus 1/2 times this constant times x of I squared. That's the harmonic oscillator. This is a spin-independent operator. You can obviously add a magnetic field, and then you will have a spin dependence as well, if you want to. There's nothing which hinders you doing that. But the point now is that we can solve that problem for harmonic oscillator. And we know that this H0 acting on this state, phi, this is little phi, not uppercase letter phi, of I, is equal to a small eigenvalue for the harmonic oscillator like that. Okay, so now comes the next. So suppose now I have an atomic neon as an example. Let's use that. You know, oh, wow, I went over time here. Sorry for that. Right? I'm getting too excited with these topics. I've been teaching these topics for so many years, but I think it's equally fun every time. And I forgot about time. You guys are too patient. You should tell me, Morten, you are going over time now. Eh? So let's just pause the recording. Okay, so before the break, we were looking at this ansatz which we made about a many-body system. And we made now the assumption that there is a part of the Hamiltonian which we can solve with that ansatz. And that part is normally set up in terms of one-body operator, which means that an ansatz for this specific state is a function which is given by a determinant. So the typical ansatz goes back to a physicist, a solid-state physicist, and one of the pioneers on physics, which is called a Slater determinant. So that means that we are going to make an ansatz. And now I'm just going to put this label lambda to indicate that this is a specific quantum state for a many-particle system. It could be the ground state, the fundamental state, or it could be an excited state. But now we just leave it undefined. So we have the positions of the particles, x1, x2, and we have up to xn here. And then there are some additional quantum numbers which now refer to the specific particles. So if you think of a harmonic oscillator, that could be in 3 dimensions, the nodes of the wave functions, which we would typically label with nx, ny, and nc. If you're dealing with a hydrogen atom, it would also again be the number of nodes the single particle wave function has, the angular moment, the orbital momentum, and the projection of the orbital momentum. So remember now that every dimension gives you a quantum number for bound states. So bound states is actually a system where, or how to say, the bound states restrict the motion of an object to specific discrete states. So we have some additional quantum numbers, which I will just label with Greek letters, alpha, beta, gamma, up to some tau. And this state here, and I'm coming back to why we have the n here, because that realizes all the possible permutations which we can have. Now, and this is given, so this is a determinant, and we are going to have a single particle state with quantum numbers alpha. And the way I'm going to label things is that a column refers to a given particle. So I have another state, beta, and then I have an x1 here. And this goes all the way down to phi of tau of x1. And then we have the next one, phi of alpha. So the rows contain these specific quantum numbers which specify a given state. And then I have phi alpha of x of n. And then we have all the way down here, phi of tau of xn. And then we have a phi of beta of x2 down to a phi of tau of x2. So this is a determinant. So we have n single particle states. So SP, this notation here, single particle. When you see this acronym, this is single particle state, single particle. Now, single particle states with labels which we call alpha, beta, gamma, up to tau. Now I'm going to be a little bit more specific, and I'm going to make a change here so that we have some specific states which we are going to use in the ordering and classification of these quantum mechanical states. Now, we have assumed now that this quantity is a eigenstate of this operator phi 0 or phi lambda, one of the specific states of H0. Now, what I'm going to introduce now is labeling. So we are going to have states which are occupied up to a given level, single particle level. So if we now think of a harmonic oscillator, for instance, you would have the first state, which has an energy epsilon 0. We have a state epsilon 1. We have a state epsilon 2. And then we go up to an epsilon n. So these are the first low-lying states. And we are making an assumption now that we can have only one fermion or one particle in each slot. So the Pauli principle has as a consequence in such a single particle picture that you can only have one particle in one specific slot. So this N0, if we now take the harmonic oscillator example, and let's say we have the harmonic oscillator in one dimension, one dim. This means that this epsilon 0 corresponds to the quantum numbers nx. And so this nx is now equal to 0. The next one corresponds to nx equal to 1. And then we have nx equal to 2, etc., all up to nx equal to n here. So these are the states which we are filling up. Actually, I should put n minus 1 here because we count with 0. So we have now n particles. So it means that we have particles in every slot here. Okay? Now we are going to assume that one type of wave function could be that we are now filling all these single particle slots up to a certain level. This is often an ansatz for the lowest lying state of the system or the ground state. Because if we now add and calculate the energy of this system, so each one of these has an energy which is given by h bar omega in one dimension of nx plus 1/2. So the total energy, since there is no interaction here, is simply the sum of all the single particle energies. So that means that the total energy, which we label with an uppercase epsilon, and I'm going to write this as an epsilon 0, because I'm going to refer this as a many-body state, which is the lowest one, or the one with the smallest value in absolute value. So this is simply the sum of I equal 0 up to n minus 1 of these epsilon i's. Okay? That sound, hope it's not too trivial, but this is just the way we are going to label states in our machinery. Now, we know that the harmonic oscillator has an infinity of states. So that means that we have more states here, but we can decide that we have a level here. So we have a continuum of states. There's an infinity in principle. But in one way or the other ones, we are going to make a truncation in the total number of single particle states. So what we could do now is simply to say that this is the ansatz for the ground state. So it means that in this type of system, as we will see when we now do the calculations, is that we can make an ansatz for the ground state, phi 0, of x1, x2, and then we have these quantum numbers, which I'm going to just label as of up to n, which I now will label as alpha 1, alpha 2, up to alpha n. So I'm going to use a labeling now, which is going to disentangle us a little bit from the harmonic oscillator, okay? So I will now think of this as an alpha 1. These are just now quantum numbers, which I leave undetermined. The previous case was just an example with the harmonic oscillator. And now I say that this state is specified as the quantum numbers alpha 1, alpha 2, alpha 3, up to a given alpha n, like that. And then since this basis is often an infinite basis, then I obviously have an infinity of states here. And then we are thinking of having one object in each slot here. So you could think now of these as specific slots where you have a set of quantum numbers. Set of quantum numbers, Qn quantum numbers. So in this case, we have n particles, and you could now just think of a string of n boxes, okay? And since these are indistinguishable particles, it means that the particle 1 can be in box 2, it can be in box 3, and so on. And the expectation value of the energy does not depend on that, because the Hamiltonian which we are dealing with and any of the operators have a invariance under permutations. Okay? So you can now think of this. So I'm just preparing for the more compact way of thinking of the way we represent a state. So we have adopted this single particle picture. So you could now think of this state phi 0, which now is x1, x2, up to some xn. So these are the quantum numbers, alpha 1 up to alpha n. And you could now think of slots here, where you have alpha 1, a new slot, all the way up to some alpha n. But this continues. So you would now have alpha n plus 1. There's a new slot here, and in every slot, you can place just one particle. And in principle, this goes to infinity, but we are going to make a truncation. And that truncation is something which I will use an uppercase letter D for, which then sets the dimension of this single particle space. And in this ansatz for phi 0, we have one particle here, one particle here, and this is just filled up to here. So this is one possible state. And we are also making the assumption, and we will see that this is an eigenstate a little bit later, that this has an energy which is just the sum of the single particle energies. So this is a problem which we can solve. And then we have an orthonormal basis. And we can use that basis to make another basis by finding a unitary transformation. So what I'm doing now is to make an ansatz in terms of a single particle picture, okay? Now, the thing which we are going to do is actually to rewrite this determinant because when we're going to run calculations now, except for a 2x2 determinant, it's going to be clumsy to actually set up integrals, which are expectation values of this monster expression, right? So everything we do now in the coming is actually us trying to find a compact notation, okay? And then we can actually rewrite such a determinant in a simpler way. So let me try to explain what is the simpler way by which we can write such an expression. And with that, we can actually simplify the calculation of expectation values. But now we have a way to set up. We are assuming that we have a single particle basis, and we are making a picture of our system. And if this state, which we have this phi 0, is a state which has a, suppose somebody gives you the exact ground state, and that state has a large overlap with the exact ground state, then you would say that this picture, using a single particle picture, actually makes sense. So suppose somebody gives you the exact state, then you could use that to motivate such a single particle picture by simply calculating the overlaps. If the overlap is close to 0, it means that this picture which you've made is not very meaningful. So everything we do is actually us making a model of physical reality. So whether that is a good description or not is something you can actually only check by having experimental data. So one thing you see now is also that, this is for later, is that when you have this kind of binary system, because these are fermions, and for fermions, you can have a slot which is either occupied or not. And this lends itself to a binary representation. So if you have 10 particles and let's say 15 slots, or let's just make it a little bit simpler. Suppose we have n equal to 4 and 8 or n equal 8 slots as an example. This means that you would have a system which looks like this. So 1, 2, 3, 4, 5, 6, 7, 8. So you could now think of one here, and one here, and one here. So this would be slot alpha 1, alpha 2, alpha 3. So these are just specific quantum numbers which you use to label the system. And these quantum numbers have often a strong coupling with experiment. So this one, if you want to represent it, you could now think of this as bit 1, 1, 1, and then 0, 0, 0, 0. That would be the compact representation of that state. And remember now that this would be the tensor product of 4 single particle wave functions. Just going back to that example which we had with 2, which we coupled together. And then we just had a representation like 1, 1, 0, 0, etc. So this is now just a way by which you can compactify the information. But let's now go back to this determinant which we had here. So this specific Slater determinant, and see how we can compactify that representation. So let's just start with, without offending you guys too much, with a 2x2 determinant. Okay, so we have a determinant which is an A11, A12, A21, and A22. Okay, so if we just write it out, what we have is obviously A11, A22, and this comes with minus A12 times A21. I can rewrite this one now as A11, A22 plus minus 1 to the power of 1 of A12 and A21. So notice one thing now. we can choose a specific ordering when we write these determinants. So I can now decide to make an ordering where I only take the diagonal elements. Okay? So I can actually rewrite this in a more abstract way. Here, only diagonal elements. So I'm going to rewrite this now in terms of a function which runs, this is a little p minus I to the power of p. And I'm going to explain what that is. So this is a little p. And then there is a permutation. And I'm going to call this a p of little p here. That's the number of permutations I can make. And I've chosen an order, A11, A22. So this p, little p, is the number. So this runs over all the possible permutations which I can make. So the permutation of two columns. So if you look at the last number which we have here, I have permuted columns 1 and 2. Can you see that? So if I permute 1 and 2, and I do the same with that one, that's a permutation. So that means that if I take this guy here, and then in the next term, so I'm running over all the possible permutations I can make. So when I have a 2 by 2 matrix, I can actually make the number of permutations. So here, little p is equal to 2. So I can I have 1, 2, which is the basic one. And then I have 2, 1. Okay? So what I'm having here is just a compact way to write the Slater determinant, where I have chosen a basic ordering. So why do I do that? If you now go back to this kind of notation which I have here, you see now that I have made an ordering according to physics. So my physics intuition is that the ground state probably, I hope, has a large overlap with this ansatz, where I actually fill the lowest lying states. And if you do go to condensed matter physics, there is often a gap here. If you go to nuclear physics, there is often a gap from the last occupied state to the first excited single particle state. Remember again that the single particle picture is not an observable in a many-body system. This is us making interpretations. If you do nuclear physics, you can actually motivate this by looking at something which is called the separation energy, where you take the energy difference between a system with 10 nucleons and 11 nucleons. And if you see such a big gap, that's a sign of evidence that there is actually a system where it requires more energy to excite one of the particles up. So we're also going in the way we talk about a system. We are not going to think of particles interacting infinitely many times, but we are going to make a representation of the system in terms of excitations above and below. And this quantity here is normally called the Fermi level. So in condensed matter physics, you often have something called a band gap. You may have heard of that. If you go to the periodic system, if you look at atomic neon, in atomic neon, the last single particle state is in hydrogen type formalism is a 2p. And it requires energy to knock out an electron from that state to an excited state, or to knock it out. So you have something like the ionization energies in atomic physics. Are you familiar with that? So ionization energy means often you knock out an electron, and then you have an atom with a positive charge, because you have an excess of protons, of positive charges. So in nuclear physics, you can knock out a proton, or you can knock out a neutron. In condensed matter physics, you have a band gap, and that's very important for the conductivity properties of, let's say, semiconductors, just to give you an example. So there are tons of examples where this kind of picture actually becomes the kind of dominating way of thinking of a physical system. So what we want now, since we have chosen an order here, if you now go back to the determinant, you will see that my order follows the diagonal element. So particle 1 in the first slot, particle 2 in the second slot, particle 3 in the third slot, etc. So I'm going to opt for an order which follows my physical intuition about the system. And when you set up a determinant, you can then choose whether you want to use this as your basic ordering of a determinant, or you could use these two guys. I mean, there's nothing which hinders you using that. But here, we couple the diagonal elements to this single particle picture. Does that make sense? So everything now deals with us finding a simple way of ordering the states. Because if you now go to, the reason we do this is if you now think of two fermions or two particles, these are the permutations which you can make. These are indistinguishable particles. So you don't know if particle 1 is in slot 1 or slot 2. There is no experimental evidence which allows you to make this distinction. So that means that we have to account for all the possibilities which you then see here. So this is actually a way where we know that particle 1 could be in this one, it could be here, etc., etc. So then we want to have a more compact notation, because if you now move to 3 particles, so if you now take a 3 by 3 determinant, we can make the following permutations. So in total then, we have 3 factorial permutations, and this will be the total number of permutations which we make. So this number of permutations then would be 1, 2, 3. That's the first one. This is just the diagonal part in the determinant. And then we have 1, 3, 2. And then we have 2, 1, 3, etc. I'm not filling in everything because this is pretty obvious. So in total, there are 6 permutations. So that means that you can write a general determinant like this, A11, A12 to A1n, and then no, that should be A21, A31, down to AN1, and all the way to ANN. You can actually write this as a sum over all the possible permutations. So you have 1 equal, so 1 is just the no permutation at all. And this goes up to the total number of permutations, which are just labeled as a P factorial. That's the total number of permutations. So if you have a 3 by 3 determinant, I can make 6 permutations. And this is going to be given by -1 to the power of I. And this is a permutation operator, I, for given permutation, multiplied, in our case, with these matrix elements, which would be simply A11, A12, no, A22, etc., up to ANN, for instance. So this is going to be the way I choose this as the basic ordering. And now I'm going to make all the possible permutations of these columns. If you go back to this 2 by 2, you see now that I have only 2 permutations. And the second one here is actually going to give me now the -1 here. And then I've permuted 2 columns. So this is a compact way we can set up a determinant. Now, there's another thing which is important for us, and that is an assumption which I'm just stating, is that the Hamiltonian of the system actually commutes with this operator. So this is also given by H0 with P, and this is also given by H of I, the interaction piece, which also commutes. So we can now actually rewrite the Slater determinant, which we had. So we can then have a Slater determinant rewritten as, and now I'm going to define some new functions. And so I can actually rewrite this, and now we're going to specialize to the ground state of the system. So we have a phi 0, x1, x2, up to xn. And then we have these quantum numbers, alpha 1, alpha 2, up to some alpha n. This is a determinant which we wrote as 1 over square root of n. And this is contains now not a sum. Let's just write the determinant as we put it up. So there's going to be a phi alpha 1, x1, phi alpha 2, x1, down all the way to phi alpha n of x1. And then I have a phi alpha 1, x2. So each column represents now a particle. And then I have 1. And then the rows represent a given set of quantum numbers or slots. And then I have an alpha 2 of x2, etc. And this is a phi of alpha n of xn. Yeah. Yes, yes. Yes, exactly. So let's go back to these 4 particles in 8 slots. So just to give an example, that's a very good point, actually. So suppose now we have 8 slots, you can place these particles. So 1, 2, 3, 4, 5, 6, 7, 8. So you could now define one determinant like this. And we would often think of that as the ground state. So now I'm just using this Dirac notation, or we can just use this phi 0 as we did before. I will often mix between the different notations. Then you could think of, since the number of ways you can distribute these states, the number of ways, total number of configurations. So this state here is a configuration of the system. So you configure the system by placing particles in slots. So when you hear things like configuration interaction theory, configuration, this is now given. So we have, in our case, we have n particles. So if you do the combinatorics, and you've probably seen this, and this is n slots or n single particle states. This is given by the standard binomial factor here, which is given by n factorial divided by n minus n factorial multiplied with n factorial. So here we have 8 slots and 4 objects you're placing in these slots. So this is just combinatorics. And that gives you in total 70 possibilities in total. So your total Hilbert space is a space of 70 realizations or 70 configurations. So you could now think of having another one. And here I will often introduce so this could be the Fermi level. And now you could have another realization where you have a state which has been promoted above the Fermi level. And then we could call this a phi 1. And then you could just continue like that. So these are all the possible realizations. Now, since you have 70 configurations, if you want to translate this in terms of an eigenvalue problem, your ground state will be, since these are orthogonal states, your ground state will be a linear combination of 70 orthogonal basis functions, which you assume are solutions to parts of the Hamiltonian. So the true ground state would be that. And if you want to set up a diagonalization problem, this would lead to a Hamiltonian matrix, and we're coming back to that, of dimensionality 70 times 70. So this is normally what we in many-body physics call a baby case. So this is something which you can do in just barely milliseconds. And we're actually going to do that. We are going to look at an example of a model Hamiltonian, which is called the pairing model. And for those of you doing nuclear physics, this is something you have met. And those of you doing condensed matter physics and having studied superconductivity, this is normally called the Badin-Cooper-Schrieffer Hamiltonian. Okay, so you see now that what we have here is something we want to write in a more compact way. And this ground state then, which I'm just going to call phi 0, and now I'm skipping all the other x's and alphas here. We can write this one now as 1 over n factorial. And then the sum over all the possible permutations, I write this as a little p, minus 1 to the power of p. And then we have this permutation operator. And this is now multiplied with a function which I'm going to put a subscript h on. So this phi of h is actually the set of single particle wave functions where I have used an ordering, where I only take the diagonal elements in the Slater determinant. So these are these little phi's. And then I have an alpha 1 of x1, a phi of alpha 2. These are only the diagonal elements. Not uppercase letter, but phi of alpha n of xn. So this is nothing but this compact way of writing a determinant. And this is physically motivated by the fact that we are assuming that there is a set of states which we fill up to a certain level. And these states are the diagonal elements. This is just one ordering. Now, why do we do that? Now, if you look at the states you have here, there are obviously many ways you can set it up. So if you look at this specific state here, you could now think of particle 1 being here, 2, 3, and 4, right? But there's nothing which hinders you saying that particle 2 is in the first slot. You don't know that. That is one possible realization in this determinant, because remember now that if you have a 3 by 3 determinant, you had actually 6 possible permutations. So you have the choice now whether you want to store all the 6 possible permutations and just have them on file and just fetch that number, or just one. If you store only one, that obviously saves 5 places in memory. So this is obviously a baby case. If you have 10 particles, you have 10 factorial number of permutations. And if you want to store that information, you will quickly just fill up your memory. So what you end up with then is a nomenclature where you decide that I want to have this specific ordering. Then it means that when you then want to fetch, instead of having 1, 2, 3, 4, but you have 2, 3, 4, 1, for instance, then you know exactly how to get that information by going back to the ordering which you had. And we will see that when we calculate expectation values. So I didn't get to expectation values, but the where we will continue next week. So this is simply done. This kind of ordering is done because you want to have a reference ordering, and then you can include all the permutations based on that reference ordering. And that saves place in memory. But you will also see that many of the expectation values can actually be calculated with this reference ordering only. So what we will do next week, and you will find that information in the slides for this week as well, is that we are going to calculate this expectation value here of H0. And we will show that if this phi 0 is based on the single particle energies, this will just be the sum of single particle energies up to the last field level, or just the sum of occupied single particle energies. So for this specific case, this will just be a sum over all the alpha i's of epsilon alpha i's, where these alpha i's go up to the last field one. So this is the single particle piece, and normally this is something which we can calculate analytically. Then we are going to calculate phi zero of the interaction piece with the same state here. And that will give us an ansatz for the ground state energy. With that ansatz we had for the ground state. This is not going to be the exact energy of the interacting system because phi zero is not an eigenstate of the full Hamiltonian. So that will be an approximation. So how good that approximation is depends on the ansatz we have made. You see the kind of, I wanted to use this kind of first lectures to give you the kind of more bird's view on the way we are going to approximate many-body systems and how we can improve upon that. So for those of you familiar with mean field theories, like density functional theory, then this Slater determinant would be given by the density functional theory solution, which is normally better than a solution which hasn't included a mean field calculation. But many of the many-body methods we will deal with are typically called post-mean field methods because you can compute additional contributions to the energies beyond the mean field. Okay. Yeah, I think this room is occupied till the end, isn't it? Yeah, we have exercises as well. Yeah. Okay, I'm going to stop the recording, but feel free to ask questions.